few ITC people to join. But
we have to explain to the Germans that 11 and
because of the tight scheduling amongst all of the events today, this event has to be out. We just basically have to be done by noon, and then we have to ask you if you have conversations and like to take them out. We need both this entire area as well as the entire area out in front, behind the doors, for doing setup for the next event. And then the next event for the Harvard Heidelberg is starts at 2 o'clock. So you only have between 2 and 3 before they needed to cut down for the next setup for the next event. So please try to be here somewhere between 5 minutes of 2 and 10 minutes to 2, so that at 2 o'clock you will be able to start. Then both of the speakers can get their full time in, and everyone will be just so happy. So let's start with this one.
Yeah. So today's ITC Colloquium speaker is Diederik Kruijssen. I think he's also speaking for the Harvard Heidelberg staff formation meeting. But for the people from the ITC who don't know him and haven't met him for the past 2 days, he's a ERC research group leader and Emmy Noether Fellow at the University of Heidelberg. He did his PhD from the University of Utrecht in 2011, and then was a postdoctoral fellow at MPA from 2011 to 2015, after which he moved to Heidelberg as a Gliese Fellow and a research group leader, and then Emmy Noether Fellow, and then an ERC Studies Fellow. So, and he's an expert on star formation across cosmic time, and today he will talk about the physics driving the molecular cloud life scale during galaxy formation and evolution.
Thank you so much, Rahul. And thank you, everybody. Is my microphone on? Should I put it higher? Is that better? It's good? Okay, thank you. Yeah, thank you so much for having me. It is, believe it or not, it's actually my first time in Boston. And so for me, this is kind of been coming for years. I really wanted to visit, and it's really nice that I'm finally here. And I'm here for the next 2 weeks. I've really been looking forward also to speak with a lot of you, and the schedule is shaping up super well, so I'm really excited about that. As Rahul just introduced, this talk is part of both the Harvard Heidelberg meeting on star formation, as well as the ITC Colloquium series. And for that reason, what I'm going to try and do is link some of the small-scale physics, or at least for many of you, small-scale physics, that we've been talking about at the Harvard Heidelberg meeting, to the more sort of traditionally large-scale physics that people at the ITC are interested in. And what I hope to show is that basically all of those scales are really talking to each other and form part of a larger multi-scale baryon cycle, at the root of which is the molecular cloud life cycle. And basically what I'd like to talk about is how that molecular cloud life cycle plays an absolutely critical role during the formation of galaxies that you see here. But before I start, I should highlight that this is not going to be a summary of my own work. It's going to be largely a summary of work from a lot of people in my group and my collaborators. I'd like to highlight 2 people in particular who are here at the Harvard Heidelberg meeting. So if you would like to talk to them instead of me, which I strongly encourage you to do, then you know how to find them. But let me start here with what I think most people think about when they talk about, say, the baryon cycle in galaxies. When people talk about the baryon cycle, they often talk about the sort of large-scale flow from star formation and feedback within galaxies, so here shown as young stellar clusters in M82, and the feedback driving outflows into the circumgalactic medium, and then that material over time cooling and precipitating back down into the galaxy, driving further star formation. And this is sort of classically the baryon cycle that people talk about. There's a huge volume of literature that tries to describe this process to explain the star formation rates of galaxies. And the basic premise behind this idea, or this steady-state bathtub model that has become very, very popular, is that basically the mass inflow rate from the circumgalactic medium sets your star formation rate, and thereby, again, through feedback, your mass outflow rate. And that this basically forms a sort of closed equilibrium system. And this model has been so popular that I need actually a lot more than 3 lines here at the bottom of my slide to quote all of the papers that have sort of advocated this idea. I think there are many hundreds of papers on this. And what is really sort of the bitter point in the context of this model is if you look at the Harvard Heidelberg meeting on star formation and the ISM that we're having this week, is the interstellar medium doesn't really play a role in this cycle. Right? You go straight from the circumgalactic medium to star formation and feedback on the small scales, and these two communicate directly with each other. And if I were the interstellar medium, I'd be really sad. I want to play too. And what I'm going to show in this talk is I'm going to do two things. I'm going to reassure all the Harvard Heidelberg people, and I'm going to tell the ITC people that this is actually really important. What I'm going to say in particular is that there's more to this picture than basically just this mass balance, this mass conservation. And what we really should try to account for is the fact that the baryon cycle is a multi-scale process that is very strongly affected by the ISM properties, by the cold medium within galaxies. So I'll start basically here at the bottom by talking about star formation and feedback and how we can understand that and its link towards the interstellar medium, basically slowly bring the interstellar medium into play. Now on the large scales, we know that star formation and feedback are really fundamental processes, because if we look at here on the left-hand side, something we understand relatively well, which is the initial conditions of the universe in the cosmic microwave background, and then the eventual growth of structure in the cold dark matter cosmology framework, the only way of actually making that a predictive theory of galaxy formation and testing it against observations is by linking in here some type of prescription for star formation and feedback. That's the only way that we can actually try and predict the observable galaxy population. And this is exactly where things get difficult, because large-scale cosmological simulations of galaxy formation need to have some type of prescription for star formation and feedback. And turns out, maybe unsurprisingly, that these are immediately the biggest uncertainties in galaxy formation modeling. So this is showing one example. This is a paper by Phil Hopkins, where these three panels show exactly the same initial conditions of a simulated galaxy, exactly the same physics, except for one thing, and that is the conditions under which gas particles in these simulations are turned into stars. So in the top panel, the gas needs to be self-gravitating. In the middle panel, it needs to be sitting above a certain density threshold. And in the bottom panel, it needs to be molecular. And you see that depending on exactly the criterion you use to convert your gas into stars, you end up with radically different galaxies. And the same applies when you look at feedback. So this is a paper that Ben Keller and I are preparing at the moment. And in this case, it's again exactly the same initial conditions. And ironically, it's actually also exactly the same feedback prescription. There's the same energy and momentum being deposited in each of those panels. The only difference is the delay time between stars forming and depositing that energy and momentum. It's the only difference, when you deposit your energy and momentum. And you see basically immediately that you completely change the morphology of your galaxy. This is how critical these problems are. This is how critical the subgrid physics of star formation and feedback in these types of simulations are in shaping your galaxies. And the critical problem too is that many of these choices really make sense. And it is not obvious ab initio what actually the right choice is. So how do we solve this? And the way forward, I believe, is to go to observations. Because, we theorists, we argue and we bicker, and we're very good at that. But the one thing we're not very good at is being right. For that, you need observers. And I think what you just saw in the previous slide is that the timescales over which those processes take place, star formation and feedback, right here in particular is a clear example of how the timescales are important. These are really the key step. If we can somehow observationally measure timescales on which these processes take place, then we can actually start to solve this problem in the context of galaxy formation. And to address that, I would like to go first to the large-scale relation between the gas surface density here and the star formation rate surface density, so the Schmidt-Kennicott relation. And on large scales, you see that this is a sort of close to linear relation between the gas mass surface density and the star formation rate surface density, where gas is converted into stars on some characteristic timescale with some characteristic efficiency. And if you measure this relation instantaneously, like here, you notice that the star formation efficiency and the star formation timescale are degenerate quantities. You can't tell based on the observed relation here whether you're looking at rapid evolutionary cycling, where the timescale is short and the efficiency is low, or at some form of quasi-equilibrium, where the timescale is very long and the efficiency is very high. You can't tell. But thankfully, as you start looking in more detail at galaxies, I think you can actually distinguish. Because in the case of rapid evolutionary cycling, what you would expect is that giant molecular clouds live for a very short time, and at some point form stars and get blown up. That's the idea of a rapid cycle. And what that would mean is that molecular clouds and H2 regions rarely coexist. Basically, you get a GMC, it forms stars, gets blown up, and then you've got your H2 region. Whereas in this quasi-equilibrium picture, you would have a GMC sitting there and forming stars for many dynamical times, such that if it forms massive stars, basically the H2 regions and the GMCs are co-spatial for long timescales. Now, what that means in the context of the star formation relation is the following. If they rarely coexist, then this star formation relation must be strongly scale dependent, because as you zoom in, at some point you will only see a GMC, or you will only see an H2 region, which means you're either sitting here with only your GMC, or you're sitting there with only your H2 region. Now, on the other hand, if we're looking at this quasi-equilibrium picture, then you might expect that individual GMCs themselves are actually following this relation, because they're just sitting there for a long time and gradually forming stars all the way along. And then it would make sense that your GMC properties actually define the rate at which they form stars. So that's the question, is as you start zooming in on galaxies, do we keep the same relation, or do we develop some kind of orthogonal scatter on this relation? Now, there are two ways, or two things necessary to answer that question. To qualitatively answer the question, we need submillimeter observations of the interstellar medium at cloud scale resolution. With ALMA, that is now possible. To quantitatively answer that question, we need some form of methodology, of interpretative framework, to actually take these observations and quantitatively translate them into the quantities that we're interested in. And I'll try to highlight both of these. So first, I'll start with the qualitative answer, and that's the power of ALMA. So what you see here, this is going to be a movie, once I hit play, is a map of star formation and molecular gas in the nearby galaxy NGC 300. So here you see an H-alpha map, and at this point the resolution is really coarse. It's 2.5 kiloparsec. So call this pre-ALMA if you wish. It doesn't quite do justice to facilities pre-ALMA, but it's a good start. So here you see the H-alpha tracing massive star formation. Here you see the CO tracing molecular gas, and this is the ratio between the two. And the ratio between the two is effectively just the normalization of this star formation relation that you see earlier, right? So basically, the fact that this is all white tells you that it's sitting on a close to linear relation with a constant ratio between CO and H-alpha flux. And as we start zooming in, the question is, does this stay white, or does it become bright red and bright blue on this scale, so that you basically get strong excursions from that star formation relation on small scales? Now, as the movie starts playing, it doesn't require a PhD to recognize that this is no longer white. Right? So what we see here immediately is direct observational evidence for rapid evolutionary cycling on the cloud scale. And what you see here on the bottom right is a way in which you can quantify this. So what this shows is this CO to H-alpha flux ratio as a function of the resolutions of the aperture size, where you focus apertures on peaks of molecular gas emission or peaks of H-alpha emission, of young stellar emission, and then how that changes relative to the galactic average. And what you see here is that there is a decorrelation. So on large scales, where basically these two are correlated, as you zoom in towards smaller scales, they decorrelate. Either you get very low CO to H-alpha ratios or very high ones if you focus, depending on where you focus. And what is interesting is there exists this sort of characteristic length scale where that decorrelation takes place. And that is despite people always saying that the interstellar medium is hierarchical or fractal or scale-free and so on. It turns out that this scale is the upper bound on the hierarchically structured ISM. Below this scale, everything becomes hierarchically structured. Above it, you're basically just averaging over your galaxy. And what I'll show later is in NGC 300, we find that this scale corresponds to the disk scale height, the gas disk scale height. So it has a physical meaning. Okay. Now, I used the fancy movie to show this, but you can actually just look at a galaxy and see this immediately. So here's the image of NGC 300 with in blue the molecular gas and in sort of pinkish color the H2 regions. And here the same for NGC 628. In blue the molecular gas, and then in orange is the H-alpha emission. And you see immediately they're not sitting in the same place. And this is again because we're looking at a rapid evolutionary life cycle. Okay. Now, I just explained how we made this type of tuning fork diagram. And what this diagram allows us to do, you see a dotted line through here, is we can fit a statistical model to this. And what that model does is it basically translates the decorrelation that you see here on small size scales to the underlying evolutionary life cycle. And specifically what it does is it uses the asymmetry around the horizontal line here to infer how long molecular clouds live relative to H2 regions. So basically, if the top branch here is flatter, molecular clouds live for a long time. If it's steeper, sitting somewhere here, the molecular clouds live for a very short time. If the overall shape of this diagram is very flat, it means molecular clouds and H2 regions coexist for a very long time scale. And then exactly where this decorrelation takes place tells you what the typical separation length is between these independent star-forming regions in a galaxy. So that is basically how you can try and translate this direct observation into all of those individual quantities. Now, I'm not going to talk about how this works in terms of methodology in more detail. If you like, tomorrow at Lars Hörnquist's group meeting, Melanie Chevans is going to give a more extensive talk about all of this. I'd also like to refer you to the papers introducing the method. This is the one that broke Monthly Notice's publication or page charges policy. So I apologize to anybody who now has to pay page charges. But what I would like to do is basically show what we can, based on what I just described, get out of this type of measurement in terms of physics. Right? So what you see here, this is the sort of face value result, is we fitted this model to these observations, and that tells us something about how cloud scale star formation and feedback takes place in a galaxy like NGC 300. So there's a large variety of different quantities that we can extract, and I'm showing all of them here as a function of galactocentric radius. And I'd like to talk you through them one by one. So first, as I said, we can get the molecular cloud lifetime basically from the asymmetry of this tuning fork diagram. And what you see here is that the data points are basically in different radial bins within the galaxy, and the gray line is the galactic average over the entire galaxy. And what you see here is that molecular clouds in NGC 300 live of the order of dynamical time. So they're very short-lived, of the order of crossing or a free fall time, 10, maybe 20 megayears. Likewise, if you look at the feedback timescale, so this is a timescale for which molecular clouds and H2 regions coexist, it is super short. It's of the order a megayear and a half. And if you compare that to what you would theoretically expect for different feedback mechanisms, you see it coincides with what you expect for photoionization feedback and stellar winds. It's very firmly pre-supernovae. Supernovae do not blow up molecular clouds in NGC 300. What you see here is this region separation length that I mentioned before. So it's basically your decorrelation scale of this tuning fork diagram. And what you see here is it's actually relatively flat as a function of galactocentric radius. And it doesn't match something like the tumor length in the galaxy, so the gravitational instability length, but it does trace very, very nicely the gas disk scale height. And that sort of advocates this sort of feedback regulated picture that the middle panel shows, is that clouds form stars and get blown up by feedback. Because what feedback bubbles do is they would push around material until they break out of the disk and depressurize. And that would basically set your separation scale in the plane of the disk, in the plane of the galaxy. Now then, because the cloud lifetimes are so short and gas depletion times in galaxies are very long, the integrated star formation efficiencies in these clouds are very low. So they only form sort of order 2 to 4% of their initial mass into stars. And because of that, conversely, they expel 40 times more mass from the clouds than is actually turned into stars. So the cloud scale mass loading factor of those systems is about 40. And then finally, by comparing the time scale over which feedback takes place to the sizes of the molecular clouds, you can derive what the velocity is at which the ejecta are being blown out. And we find typical velocities of order 10 kilometers per second, which is remarkably close to, say, the sound speed in ionized gas or ionization front velocity. So this is actually, again, is a measurement that really makes sense physically, but we obtain all of those measurements from a single observable, and that is this typical tuning fork diagram. So what is nice about something like this, for instance, is it's basically a prediction for direct eye of view measurements. Like if you observe ionized emission lines, you can actually go and test this. So that is interesting. Okay, so this is one galaxy, but the great thing now with ALMA and MUSE and so on is you can do this for large samples of galaxies. So this is work that we've been doing in the context of the FANGS collaboration. There are 4 FANGS people here in the room. And what FANGS is doing is a very large collaboration mapping as many galaxies as possible in the local universe at molecular cloud scales, so sort of arc-second scales. And specifically what we're trying to do with that is try and understand this evolutionary life cycle of clouds as a function of the galactic environment. And there were huge efforts going on with an ALMA large program where we're targeting 80 galaxies, a MUSE large program where we're targeting 20, and an HST large program where we're targeting about 40. So in this context, Melanie Chevans has now carried out the first analysis of a sample of 9 galaxies to basically see, okay, what does this molecular cloud life cycle look like? And it turns out, across these 9 galaxies, we have about 10,000 GMCs and H2 regions, which all exhibit this universal decorrelation between clouds and young stars on small scales. And if you translate that into evolutionary timelines, then what you see is you get typical cloud lifetimes here in orange, or orange plus purple, of the order 10 to 30 megayears. But you also see that there's considerable variation between galaxies. And it turns out, and Melanie will talk about that tomorrow, that this is related to different dynamical environments, different gas pressures, and so on. So there are actually reasons why you see this type of environmental variation. Now, if I just tabulate those numbers, again, what I mentioned is we get typical cloud lifetimes between 10 and 30 megayears, which is of the order a dynamical time again. Which dynamical time is a good question. It can be an internal dynamical time that typically happens in low surface density environments, or a galactic dynamical time, which typically happens in high surface density environments. And Sarah gave a talk about this morning. This is basically, these observations are consistent with her theory for dynamical cloud lifetimes in galaxies. Then, as I mentioned, feedback is typically short. We saw that in NGC 300, and here we see the same thing. So clouds are destroyed by feedback within sort of 1 to 5 megayears. And that is predominantly pre-supernova feedback, which typically starts after only 4, maybe even longer if the IMF is not well sampled. And again, what we see is that the typical regions within galaxies on which these evolutionary cycling processes take place are separated by, say, 100 to 300 parsecs. And again, in NGC 300, this is the gas disk scale height. We've not figured out yet if that's true for those galaxies as well. So we don't know that yet. That's an open question. Here again, we see typical feedback outflow velocities of the order the ionized sound speed, which is again encouraging. This is a prediction for IFU measurements. And we see integrated star formation efficiencies that are, again, low, of the order 4 to 10% in these cases. And this is actually really encouraging if you compare these to recent theoretical work or simulated simulations by, for instance, Vadim talked about it this morning, but also the group of Hopkins and Ostreicher are basically finding very similar numbers in GMCs with similar properties to the ones we study here. So to summarize those results, what we see here from the FANG sample is that star formation is inefficient within molecular clouds due to GMC dispersal by feedback. So feedback basically blows up the clouds and therefore limits the star formation efficiencies. So if we go back to the question I asked in the beginning is okay, what drives the Schmidt-Kennicott relation? This is the answer. It is rapid cycling. It is basically an ensemble average over many individual building blocks that undergo these rapid life cycles. So if I go back to the overarching question here, okay, what does this Baryon cycle look like? The first thing that's obvious now from what we've looked at is that star formation and feedback don't directly go into the CGM. They need to do a lot of work in first disrupting the interstellar medium. So wherever that arrow goes, it doesn't go straight there. Now, how can we learn more about how these feedback mechanisms actually affect the interstellar medium? Well, the first way in which you can do this is you can actually just take those observational empirical results and translate them into subgrid models for galaxy formation. And this is work that Ben Keller is now doing in Heidelberg, where he's basically taken the observables that we get. So here's the feedback timescale, which is of the order of 1 to 5 megayears, as I mentioned. And here's the typical radius of the GMCs that we identify. And these are the typical volume densities in which the feedback goes off. And these are all observables. These are things we can measure. And they basically together define a terminal momentum input per unit stellar mass that we can feed directly into galaxy formation simulations. So what we've done here is we've taken the observations and turned them into subgrid recipes to basically solve the problem I showed in the beginning. And what is interesting here is that this is the result for NGC 300, where the data points are in red as a function of galactocentric radius. We see here that the specific momentum injection rate is relatively constant. But it doesn't coincide with any of the sort of other horizontal lines, which are naive expectations that you would have based on single mechanisms like radiation pressure or stellar winds. And the reason actually makes sense. Feedback is not a simple process due to like a single factor blowing up your cloud. It's a nonlinear combination of all of those different feedback mechanisms. And it's really challenging, difficult, to try and combine all of those mechanisms in a single recipe. So this is one of the reasons why we've gone to observations, is to say, okay, we give up. We have no idea, so let's just go to the real universe, get the right answer, and cheat. Right? That's better. Okay. Notwithstanding, I know there are lots of people who are doing great work and actually trying to understand this in detail. But if you're doing galaxy formation, then your career is over by the time you've solved that. So this basically is a pragmatic way forward. So this is one way of dealing with it. If you don't want to put in the right answer by hand, then what you can do is you can go to simulations and turn it around. Say, okay, well, this decorrelation that we see between molecular gas and young stars is actually a fundamental test of your feedback recipes in simulations. And this is work we've done with Yusuke Fujimoto, who was at the time a postdoc working with Mark Krumholtz. He's now a Carnegie Fellow in Washington at DTM. And this is one of Yusuke's simulations of an isolated disk galaxy with feedback from supernovae, photoionization. And what is nice about this simulation is that all macroscopic quantities of this galaxy are perfectly in agreement with what you would expect for a galaxy like this observed in the local universe. And not just that, the molecular cloud population of this galaxy does exactly the right thing. It's sitting on the Larson relations, has the right radius distribution, mass distribution, and so on. But if we look at this decorrelation, it's not there. So the open symbols here are what we observe in NGC 300, and the solid symbols are exactly the same measurement for this simulation. And the reason it's not there is that the feedback is too inefficient. It cannot blow up the clouds. So the clouds are just sitting there, forming stars, and they're sitting there forever, all the time. So when I showed this result to Mark Krumholtz, he was not quite as happy as I might have hoped. But there's good news, because there was somebody here in the audience who came to the rescue. So what Sarah did after we found that result in Heidelberg, she went to her simulations and said, okay, what is it exactly that is driving this problem? And she realized it was basically because the H2 region feedback was too inefficient. So she developed a new algorithm to more efficiently inject the momentum from H2 region feedback into this simulation. And what you see now here on the right is that we do get this decorrelation. It's not the same shape as NGC 300, but as I already mentioned, a lot of this is environmentally dependent. And in fact, if we overplot Melanie's measurements here for M51, they actually follow this really nicely. So in terms of the cloud life cycle, this is an M51 analog, the simulation. That's basically what we're seeing here. And with this new feedback model, it's not only that the simulations match the observed decorrelation, but as Sarah showed this morning, they also match the properties of the GMC population with reasonable distributions of GMC sizes and masses and so on. Now, because this is a simulation, you can then go in and ask, okay, why is this actually the case? So we know that we put in better feedback, or better is the assumption, but why does this work so well? And what Sarah did is she developed this algorithm to track molecular clouds in the simulation, basically trace exactly how they evolve in that context. And that allows her to create a merger tree. So this is a merger tree of just a large number of molecular clouds in this simulation. And what you can then start to do is you can say, okay, well, how long do they live? So here's a cloud that lives for 9 megayears, but it's complex, right? You see here that clouds merge sometimes or even split. So you need to think a little bit carefully about how you would define lifetimes. But once you do that, you can start to assess, okay, what is it? What are the physical mechanisms that eventually determine and define the lifetimes of the clouds in these simulations? And what Sarah did is she defined basically this fundamental parameter space set by basically the rotation curve and the gravitational stability parameter, 2 mer Q, over which she expects the molecular cloud lifetime to vary under the influence of galactic dynamics. And what she finds is that at low gravitational stability, so low 2 mer Q, the clouds are very short-lived, basically because they gravitationally collapse, form stars, and are immediately blown up by feedback. So exactly the same picture that we're getting from the observations is being retrieved in those simulations. So I think this is a very encouraging way of saying, okay, you can develop in parallel the observational measurements as well as the simulations to try and make sense of those measurements. And we're now seeing exactly the same behavior in both. So what we're seeing, is going back to this picture, is that this outflow rate from star formation and feedback on the cloud scale, the first thing it does is it affects the interstellar medium. And as the feedback energy is then stuck in this interstellar medium there, of course the question is, how do I go and populate my CGM? How do I drive outflows from galaxies? And it turns out there, again, the ISM properties are absolutely critical. And the key insight that made us realize that was one by Ben Keller. And what he realized in a recent paper that came out earlier this year is that outflows from galaxies can be buoyant, which means that they're not ballistically launched. It's not like you impart some momentum and you set them off and you wait until they fall back again. No, if the entropy of a hot bubble coming out of a galaxy disk is larger than the entropy of the gaseous halo at that radius, then the outflows become buoyant. They're basically constantly being lifted by the surrounding medium until at some point they reach equilibrium. So the entropy of the bubble becomes similar to the entropy of the circumgalactic medium. Now you can calculate the entropy of the bubble at breakout as follows, and then compare that to the entropy of the halo at the virial radius. And basically, if this is larger than the entropy at the virial radius, you can drive the bubble all the way out of the galaxy. And that would be a very efficient way of basically regulating the large-scale baryon cycle within galaxies. Now, what's the critical point here is that you see that this feedback bubble entropy that you start with is set by the gas disk scale height, which is your ISM properties, and the volume density, so the number density of the medium that you detonate in, which is again is your ISM properties. So if we do not really understand how the ISM is structured, we have no idea how to drive outflows from galaxies. That's the fundamental message here. And in particular, what we find if we look at those equations here, we see that at low ISM densities and in low mass halos, we get very efficient, buoyant, entropy-driven outflows out of galaxies. So basically, the critical mass here is of the order Milky Way mass. So Milky Way mass and lower is where you basically can very efficiently remove material from your galaxies. And as I mentioned, the cloud scale physics of the interstellar medium are critical, but in particular of early feedback, because early feedback is going to determine what the density structure is in which your supernovae detonate. If you don't have early feedback by photoionization, your supernovae go off in a dense medium and you can't drive outflows. That is basically the implication. So what you can do is you can basically write down the equation of motion. So apologies to the observers. I'm going to keep this I'm going to turn this into a Lego equation. So here are 3 building blocks. So you can derive an equation of motion where you have a term for buoyancy that basically determines the acceleration due to the entropy difference that I just described. Then there is a term because of self-gravity that's pulling everything down. And there is a term because of drag, because you're running into other material in the halo that slows you down. And if you solve this equation of motion, this is what your sort of trajectories of the superbubbles look like. So this is as a function of time, showing the height above the galactic disk. If it's just energy driven, so ballistic, you launch them once and that's it. Or if you account for this entropy driving where the bubbles are buoyant. And the first thing you notice is that here, if the bubbles are ballistic, they fall back in less than a gigayear, just a few hundred megayears. And they don't get very far. It's only of the order 30 kiloparsec or so above the disk. Whereas if they're now entropy driven, they never really fall back, but if they do, it's of the order many gigayears, and they reach almost the virial radius. So this is a much more efficient mode of driving outflows from galaxies. And you can calculate the cooling time of those bubbles as a function of the density that the ambient density that they detonate in. So this is showing here again as a function of time, showing the cooling time with evolutionary tracks for those bubbles. So these are hot bubbles that go off in low ambient density. So here early pre-supernova feedback has done its work before the supernovae go off. And what you see is basically the only time that the bubbles finally manage to cool is after 3, 4, 5 gigayears. Whereas if they now go off in sort of a 10 particle per cc ambient medium, so a low density GMC, they cool already after 30, 40 megayears. And they never make it out into the halo. So this is again evidence that ISM structure really governs the escape of galactic outflows. Now so far this is an analytical theory. You can actually go into a cosmological zoom-in simulation and ask, okay, does this actually work? And this is now showing the entropy profile here as a function of galactocentric radius of the ISM in both the galaxy and the halo. So here, this track is basically the cold galaxy disk, so it has low entropy. And this here shows the circumgalactic medium. And this is here is the virial radius. And these particles are basically just tracked to see what their entropy evolution looks like. And every now and then they get shot up there. That was feedback. So feedback shot them up. They end up here in the halo, have high entropy. And because their entropy is so high, they gradually increase in radius until they reach equilibrium, and then they come down again, rain back onto the galaxy. And it's the ISM properties that determine how far they get, and therefore also, as they expand, how far they get before they reaccrete again, before they cool and reaccrete. So it's not just that the ISM properties set the outflow, actually also in the end determine the reaccretion rate, so determine the inflow rate back onto the galaxy again. So if we go here, the interstellar medium plays a key role in populating the circumgalactic medium. And in turn, the circumgalactic medium first accretes back into the interstellar medium. And at some level, this is a closed system. And then the interstellar medium will communicate again to star formation and feedback, is the idea. Okay, so let's say now we've reaccreted, and our material has come back onto the galaxy. What does then happen? Is it just the inflow rate here that basically does directly set star formation and feedback, or is there again some type of property of the interstellar medium that determines how quickly the ISM form stars, how quickly GMCs form stars? And this brings me to basically the way in which star formation is typically expressed in galaxy formation simulations. So we've seen this equation before this morning. I was not aware of this. This is independent, but Vadim and I have sort of the same two slides now in our talks. But this is the way in which star formation is typically expressed in simulations, very similar to the Schmidt-Kennicut relation. So you have some volume density of gas that's turned into some volume density of stars on some characteristic timescale here, which is the freefall time. And we've seen from the observations that the freefall time is a reasonable star formation timescale, right? Because clouds live for the order of dynamical time. And then the efficiency on which that gas is turned into stars is some efficiency per freefall time. And what simulations usually do is they adopt a constant star formation efficiency per freefall time, even if between simulations that number varies wildly, right? So there are simulations that use 1%, there are simulations that use 100%. But if you look in detail at sort of turbulent box simulations of star formation in molecular clouds, of course this efficiency is not constant. We know that it depends on all kinds of environmental factors. So here's shown a figure by Padawan that shows how this star formation efficiency per freefall time varies with the virial parameter. You see that in highly supervirial clouds, the efficiency per freefall time is extremely small, whereas in low virial parameter clouds it can be quite high. So this is one way of expressing this epsilon FF here that would be a better representation of star formation in, say, a galaxy formation and evolution context. So this is basically the expression that was fitted in the figure that I just showed. Now there's another way of looking at this. As you heard before, I'm a fan of observations because they're right. And one of the things we've done with FANGs is we've looked at how this star formation efficiency per freefall time varies with environmental quantities. So this is again now showing this efficiency per freefall time as a function of the molecular gas surface density sort of averaged on large scales. And what you see is that in larger surface density environments, this epsilon FF decreases quite rapidly. So the typical proportionality you would find here is that basically as you go to higher surface densities, it's basically an inverse linearity dependence. So these are two examples of how you could do better, how you could go away from this constant efficiency per freefall time. And what I'll do now is I'll show what happens if you use the first one in galaxy simulations. And this is work done by Jindra Genzior in Heidelberg. She's a PhD student working with us. And she's basically looked at how this star formation prescription for the efficiency per freefall time affects the Schmidt-Kennicut relation in simulated galaxies, and in particular how that connects to galactic morphology. And there are many panels here, but I'll slowly talk through them. So in these two panels, so this is again, all of them are just showing gas surface density versus star formation rate surface density. In these two panels, we explicitly put in the galactic scale star formation relation on the cloud scale. So we're using a constant epsilon FF that is chosen to reproduce Schmidt-Kennicut on large scales. And then there are two differences here. This galaxy does not have a bulge, and this galaxy does have a bulge. Then all the other panels here use this local model that comes from turbulent box simulations where the efficiency per freefall time decreases with increasing virial parameter. So basically star formation gets shut off in strongly supervirial clouds. And then as you look at all of those different panels, the bulge strength or the bulge depth increases towards the bottom right because we vary both the mass fraction in the bulge, which increases towards the right, and then the compactness of the bulge. So the bulge gets smaller as you go down. So there's no bulge, and then basically the density of the bulge increases here. And what you see immediately is when you include a model that accounts for the virial parameter dependence of the efficiency of star formation, bulges strongly suppress star formation. You basically end up with a Schmidt-Kennicott relation that strongly deviates from what you would get without a bulge or with a constant star formation efficiency per freefall time. So this shows you again how the ISM structure, the ISM dynamics, can strongly influence what your galaxy at large is doing. So it's not just the inflow rate onto the galaxy that determines what's happening. In fact, this galaxy doesn't have an inflow rate at all because it's an isolated one. But you see immediately that there's a strong trend. And this is important because observations actually show this. So this is a Schmidt-Kennicott plot from Tim Davis's work where he's looked at early type galaxies. And these early type galaxies have strong, deep gravitational potentials, strong bulges or spheroids. And you see that in these environments, indeed, the star formation rate falls below the Schmidt-Kennicott relation that you expect for galactic disks. And this is for a very similar reason. Now, what is that reason? In the simulations, again, you can go and check. And I think this is probably the most visually striking result out of this experiment, is as you look at those disks, you go towards deeper, more prominent bulges, you see that the gas disks become extremely smooth. And the reason is that the high shear rate in those deep potential wells basically stabilizes the disk, smoothens it out, and suppresses the formation of substructure. And because there is no substructure forming, the star formation rate remains low. So there's a direct interplay between galactic dynamics, cloud dynamics, and their star formation potential that eventually ends up determining how much star formation you can get. And again, if you go to observations, this is what a typical gas disk in one of those early type galaxies looks like. This is not comparable to the spiral galaxies that we're used to seeing from ALMA. This is completely smooth. And it's for exactly the same reason. So with these types of experiments, you can now actually try to understand where these sort of strange star-forming environments or non-star-forming environments come from. And it seems again that ISM structure plays a critical role. And it is not just the structure of the galaxies, but it's actually where they sit in terms of the galaxy population. So this is showing the galaxy main sequence here in the bluish data points. So this is the specific star formation rate, so the star formation rate per unit stellar mass, as a function of the stellar mass of the galaxy. And the simulations that I just showed are sitting right here. So you see that some of them are sort of sitting on the main sequence, other ones are falling far below. And the reason they're falling far below is that we've got this wide variety of bulge surface densities or densities, depth of the potential well. And I'm not showing it here yet, I'll do here on the right in a moment. But of course the naive expectation is that these data points here at the bottom are the ones with the deepest potential wells. And the ones here at the top are the ones with puny bulges that don't really differ from these galaxies. So to quantify that, this is now showing the offset from the main sequence. So basically just the delta distance relative to the black line here as a function of the stellar surface density in the center of those simulations. And the simulations fall right here. So you see this very nice trend of basically offset from the galaxy main sequence that is basically set entirely by the depth of the potential well. Now, of course, you would argue, well, why is it sitting here? There are galaxies sitting there, there are galaxies sitting there. There's one parameter that we've not varied in this experiment, but we are in the follow-up paper, and that's the gas fraction. So if your gas fractions go up, you don't care about dynamics as much anymore because your clouds can become self-gravitating more easily and you're basically sitting on the main sequence. As your gas fraction goes down, you start to have this track going off the main sequence until at very low gas fractions you become completely quenched and you're sitting here. So what this shows is that there is a fundamental interplay between morphology, physics of star formation and ISM structure, and where galaxies are sitting in the context of the galaxy population at large. So going back, yeah?
Actually, there are some RP here. So is this like a scale radius of your bulge?
Yes, that's right. That's the scale radius of the bulge in the simulation.
That's strange because I would imagine that when you increase the scale radius of the bulge should be more important, right? But apparently it's vice versa because it's just increase the star formation,
That's a very good question. So the reason that as you increase the scale radius of the bulge, it becomes less important is we don't change the mass in the bulge. So the mass fraction of the bulge stays the same. So if we increase the scale radius, its density decreases, and it basically drowns out against the disk in the background. So it's a relative question here. Is if we were to make the bulge larger and we want it to be more prominent, we would also need to increase its mass. And we're not doing that. We're treating these as independent quantities, and that is why. So basically, in the end, you're interested in the depth of the potential, which is m over r. And if m is constant, then a larger r means it becomes less important. Okay. So if we go back here to the bigger picture, what we see is not the inflow rate, at least not exclusively, that sets the star formation rate, but it's the ISM structure. So it's basically the structure of the ISM in combination with galactic dynamics and cloud scale physics that determines how efficiently your galaxy forms stars. So going forward, I hope at this point I convinced you that there are a lot of subtleties that are actually critically important in the context of this large-scale baryon cycle. At this point, of course, the question is, how do you put this all together in a framework for galaxy formation? And that is what we're now doing in the context of the EMP simulations, which stands for empirically motivated physics. And this is a new generation of galaxy formation simulations that we're carrying out with EREPO. And it includes explicit ISM cooling, and we're tracking the abundances of 36 chemical elements and their isotopes to be able to do galactic archaeology in the long run. We do not have an equation of state, but as I mentioned, explicit ISM cooling basically allowing us to track all of the ISM phases. And the star formation model is this virial parameter-based star formation model that I just showed towards the end. The feedback model, or at least for early feedback, we're putting in based on the observations that I showed from FANGS and NGC 300, based on the observed molecular cloud life cycle. So again, we're putting in the right answer. We're cheating. Then it includes a subgrid model for star cluster formation and disruption. I've not talked about that at all. I'm going to give a colloquium about that at MIT next week, but I realize nobody from here actually goes to MIT colloquia, so, you know. Oh, wait, I'll talk about it for 10 minutes during the luncheon after this. So if you're interested, you can also come talk to me. And basically the idea is that with this set of simulations, we can go back and actually try and bridge what I showed in the beginning, this gap between cold dark matter cosmology and the observable galaxy population by putting in the cloud scale physics of star formation and feedback in a way that is empirically and physically motivated. Okay, so that brings me to my conclusions. I showed in the beginning that this is basically the prevalent view on the baryon cycle in galaxies, and I hope to have convinced you that we have good reasons to think it's not that simple. And there are a lot of important physics in all of those individual steps that communicate, that drive important differences in terms of the structure and evolution of galaxies on both small and large scales. And the only way forward, the big challenge really, is to understand all of those mass flow terms and how they mutually interact. And together then eventually constitute this multi-scale baryon cycle. And thankfully for all the Harvard Heidelberg people here in the room, the ISM is critical in all of this. Critical. So I think what the main step forward, or the main step that has basically motivated a lot of what I talked to you about today, is to not see the Schmidt-Kennecut plane as a static plane. Right? So individual clouds are not sitting in here forever. They're moving. And how we should see the Schmidt-Kennecut plane, even on galactic scales, is basically a luminosity-weighted average of cloud scale, environmentally dependent dynamical processes that are just a collection of small units undergoing rapid evolutionary life cycles. And what is interesting and exciting, I think, is that there is a spatial scale that defines those units. So we can kind of start to pin down what those sort of cycling building blocks are within galaxies. And the rate and efficiency of the important star formation and feedback processes within those building blocks are sensitive to the large-scale equilibria. They care about how much gas you feed onto your galaxy and how much of a global outflow rate there is. But in turn, those small-scale processes actually set the rate of those larger-scale processes. And this multi-scale system is what we need to understand. So where we've kind of for decades have been talking about, okay, what sets the slope of the Schmidt-Kennecut relation, what sets the normalization, and so on, it's actually really the scatter around this that traces the underlying physics. And that's what we should be focusing on going forward. Okay, so I'll conclude, and you know, to make Alyssa's life easier, I'm not presenting conclusions, but tweets. So go ahead. I think there are the following sort of key points coming out of this talk. The galactic baryon cycle is seated on molecular cloud scales. And if we want to understand the baryon cycle, that is where we need to go. I've shown that molecular clouds live for about a dynamical time, and they're truncated their lifetimes by early feedback, which results in very low star formation efficiencies. Because of that early feedback, you can get buoyant, entropy-driven outflows that efficiently make it out into the circumgalactic medium, but only if early feedback and the ISM structure allow them to do that. Then coming back and flowing back onto the galaxy, the ISM structure suppresses star formation in stellar spheroids, and that drives actual physical offsets from the galaxy main sequence that are entirely set by cloud scale physics, and that is independently of the accretion rate, of the inflow rate onto the galaxy. And then finally, we're putting together all of those insights into the EMP model to eventually translate them into the realm of galaxy formation simulations. And as I said, I'll be around for, another 7-8 days. And if anybody is interested in talking about any of this, I'm really excited and looking forward to talk to you. So thank you for listening.
Thank you, Diederik, for the very interesting questions.
I have a question about the third point. So,
Yep.
is the interpretation that the star formation in the center is lower because strong shear drives stronger turbulence? So, is this connection? Efficiency is lower because
so at some level, indeed, the shear drives stronger turbulence, and that drives up the virial parameter, and therefore the efficiency per free fall time goes down. But I would say that there's a step in between that plays into it as well, and that is that because of the strong shear, you suppress substructure formation, right? And the lack of substructure also keeps your virial parameter up. So it's not just your velocity dispersion term, but it's also your m over r term in the virial parameter that plays a key role. So it's both.
So that was very nice, but I have questions about the end scales, beyond the ends. Okay? So the last time I checked, H2 regions form in molecular clouds. So at very small scales, this must be different.
Yes.
And then at very large scales, the structure of the galaxy itself
Mm-hmm.
and the changes in the thickness of the galaxy, whether it's either waving or warping or
Yep.
flaring or whatever, probably also matter. And so I'm just curious, is that 2020, 2021? When do you include the really small scale effects and the really big scale ones?
So at some level, okay, this is a great question. At some level, it's already in there. At some level, it's beyond the scope of this work. And the reason is the following, is this separation length that we identify here is the upper bound on the hierarchy that you're alluding to, right? So this basically sets your individual building blocks that then each are hierarchically structured and each will have their individual micro H2 regions, which we don't care about, but there's a reason for that. And the reason is that we are agnostic here in this framework about what a GMC is or what an H2 region is. What we're really measuring is the lifetimes and the feedback timescales of what we call independent regions. And what these are regions that are sitting on this evolutionary timeline in a phase, in an evolutionary phase, that is independent, is uncorrelated to that of their neighbors. And that is important because it means that those are the building blocks you can sort of describe in terms of an evolutionary life cycle. Now, if you have a GMC that represents one of those independent regions that has, say, 3 H2 regions, I would argue that those H2 regions are not independent. They're correlated in terms of their evolution because they're formed out of this same GMC that exists at that moment in time. If they were coming from a different GMC that came into life independently, then they would be independent, right? So for the purpose of this framework, those 3 H2 regions are the same H2 region. Doesn't mean you can't play the same game on smaller scales. So you can say, okay, well, I'm looking at a GMC. Now I want to know what my YSO lifetime is, and you can do exactly the same thing, right? So there is a multi-scale version of this that you could look at. Now on the large scales, what you mentioned is when do galactic morphological features kick in? So in the context of this framework, they don't really. And the reason is this convergence here happens on size scales above which morphology becomes important. So basically, galactic morphological features are important on the scales where you've already averaged over a sufficiently large number of regions that you've basically converged onto your Schmidt-Kennecker relation. The one way in which you can look at that is say, okay, well, let's make morphological masks look at parts of galaxies where we try to infer the cloud life cycle. And this is something that I'm sure Melanie will talk about tomorrow, is cloud lifetimes are different at the co-rotation radius, in bars, at bar ends. Not as much in spiral arms. It turns out spiral arms don't do that much, and I think that's consistent with Sarah's work as well. So that is one way of doing at this, of looking at this observationally. I think theoretically what Sarah is doing is exactly what is necessary in that context, is making that link between galactic dynamics and the cloud life cycle, and making that explicitly in a numerical and theoretical context is probably the future in trying to understand this. But that is work in progress.
So this bathtub model is one of these models that explains everything and therefore explains nothing, right?
Yeah.
And so you're putting in these intermediate step, which has more to do with the physics. But in some sense, it's okay to consider that, like the bathtub model, you sort of just short circuit your interstellar medium.
Mm-hmm.
And if the time scales are small for that step relative to, say, the mass inflow rate and the outflow rate into the certain galactic medium. And so then I'd say, well, in your entropy-driven model,
Mm-hmm.
I thought you were saying that the gas doesn't flow back into the disk in some sense. Now, how does this work then?
So eventually it does.
Why does the bathtub model say m dot is equal to
Mm-hmm.
the star formation rate? So how did that come about? Why does that work?
So you're asking two different questions, I think. Is one is how can you reconcile this picture with the fact that at some level the bathtub model does work?
So
And what is the added value of actually doing this? Right? So these are two different questions.
I'm okay with the added value because it's good to explain some of the physics. But
Right.
first question.
Okay. Why does the bathtub model work at all at some level? Well, I think the answer is if you look at large number statistics, you're aided by the central limit theorem. You're no longer interested in the exceptions, but you're interested in the broad brushstroke rules. And one of the things I showed, for instance, in the last bit of the talk is if you increase your gas fraction, then this step doesn't matter that much anymore. But once your gas fraction drops, it does matter. So you've got a larger diversity of regimes, of physical regimes, where you care about those different subsets. If you look at the galaxy population at large, especially at high redshift, where a lot of the properties of the galaxy population are being set, gas fractions are high, and galaxies are being, they're like geese, they're being force-fed by gas, and they need to do something with that, right? And they turn it into stars and blow up everything again. And that type of equilibrium picture, I think, makes a lot more sense at high redshift than it does in the local universe. So that, at least, I think, is part of the answer to your question, is if you set a lot of the properties of your galaxies at high redshift, then at some level a pseudo-equilibrium model should work. But it can't explain the full variety of the galaxy population, and it definitely cannot apply at low redshift.
To ask it more specifically,
Okay.
this m dot inflow that you've got there,
Yeah.
In your entropy-driven model, doesn't look like there's a lot of inflow coming back. Right? It's buoyant and it's sitting there above the galactic plane or oscillating or whatever it's doing.
Yeah, I need to forward this a little bit, and I realize that Rahul is getting a bit nervous because of the clock. But sure, they spend a lot of time there, but that's in a Lagrangian way, right? That's an individual element. If you've got a large enough reservoir, it's still coming in. And I think the key question here is, and maybe that's what you're getting at, is that there is a rate for all of those processes. And in the end, if you increase your time scale, you decrease the efficiency kind of implicitly, right, by changing the cycle here.
So then I would understand my question. The answer to my question is that the residence time in the intergalactic medium is very high.
Exactly. That's the right way of looking at it. Yeah.
Okay, now we have to stop here. And we can talk to you later.
Okay. Thank you. Yeah, because I'm giving the talk during the lunch. Yeah. Right. Yeah.
So, yeah, see you later.
Cool. Yeah. Cheers.
At some point, could we have a look at your numbers for the terminal momentum ratio? Because I forgot to make a note of them. I mean, this is one of the things we predict with It's interesting to see how well we.
No, it makes sense. I mean, this is really early days, so I had to convince Ben that I could show them. But so they might move around a little bit.
Yeah, I mean, it'd be interesting to know, like, for the different models, are we in the right?
Exactly. Yeah, I think that makes a lot of sense.
You might have noticed I was nodding enthusiastically when you were saying the problem is feedback is a whole not a linear thing. This is precisely what
I did notice that.
I'd also added the other problem is it depends on mass.
Yes.
Like,
Thank you, Erica.
things that are going to blow up Orion are not going to blow up.
That's right.
Yeah,
clearly.
so if you're looking at the whole population of the galaxy and averaging over everything,
Yes. Yeah.
that's the,
No, I agree. I agree. I completely agree with that. So that is why kind of the ensemble. Yeah. Yeah.
Really nice.
Thank you.
Yeah.
You never hear me talk about stuff like this.
Exactly. I was like, wow, you're doing all this too.